For centuries, humans have gazed at Mars, a bright red dot in the night sky with wonder and curiosity. The planet's striking color, visible even without a telescope, made it a focal point of mythology and speculation. Ancient civilizations wove tales of war and fire around it, naming it after their gods of war. As our understanding of the universe grew, so did our fascination with Mars. It became a symbol of the great unknown, a possible abode for life beyond Earth. The invention of the telescope brought Mars into sharper focus, revealing tantalizing surface features that hinted at a dynamic world. We observed polar ice caps that grew and shrank with the seasons and vast dark regions that some astronomers mistook for oceans. For a time, the idea of Martian life, perhaps even intelligent beings, seemed not so far-fetched. Though our understanding evolved, the allure of Mars never faded. It remained a powerful symbol of our cosmic curiosity and our yearning to find life beyond our own pale blue dot. While the question of whether life currently exists on Mars remains open, we have discovered compelling evidence that the planet may have once been habitable. Rovers like Curiosity and Perseverance have explored ancient Martian lakebeds and river deltas, finding geological formations that could only have been created by flowing water. Water, as we know it, is essential for life as we understand it, making these discoveries incredibly exciting. Even more intriguing is the discovery of organic molecules in Martian rocks. These are the building blocks of life, and their presence suggests that conditions on early Mars could have supported the formation of simple life forms. While this is not definitive proof of past life, it strengthens the case that Mars was once a much more hospitable place than it is today. These findings have fueled our imagination and scientific inquiry, pushing us to look deeper into the Martian past for further clues about its potential for life. One of the leading theories for the disappearance of a potentially habitable environment on Mars centers on the planet's thin atmosphere. Unlike Earth, with its thick protective blanket of gases, Mars has a very thin atmosphere, about 100 times thinner than ours. This thin atmosphere has a number of crucial consequences for the Martian climate and its ability to support life. First, the thin Martian atmosphere provides little protection from harmful radiation from the sun. This radiation can be detrimental to life as we know it, damaging DNA and making it difficult for organisms to survive on the surface. Second, the thin atmosphere means that Mars struggles to retain heat from the sun. This results in extreme temperature swings on the planet, from frigid nights to surprisingly warm days, making it a challenging environment for life to thrive. The thin Martian atmosphere paints a picture of a planet struggling to hold on to the elements necessary for a habitable environment. Another factor that might have contributed to the demise of a potentially habitable Mars is its distance from the Sun. Mars is farther away from the Sun than Earth, which means it receives less solar energy. While this alone might not be enough to render the planet completely inhospitable, it plays a significant role in regulating the Martian climate. Over billions of years, the Sun's energy output has changed. Early in the solar system's history, the Sun was slightly cooler than it is today. It's possible that Mars, in its early history, received enough solar energy to maintain a warmer, wetter climate, potentially suitable for life. However, as the Sun gradually warmed, Mars, with its thin atmosphere unable to trap heat effectively, might have experienced a runaway cooling effect. This cooling could have led to the freezing of its oceans, if they existed, and the thinning of its atmosphere, making it the cold, dry desert we see today. Section 5. The Wrath of the Cosmos, Impacts from Outer Space. Unlike Earth, which is shielded by a robust atmosphere and a strong magnetic field, Mars is more vulnerable to impacts from asteroids, comets, and other space debris. The planet's surface is pockmarked with craters, evidence of a long history of bombardment from space. While Earth experiences similar impacts, our planet's geology and atmosphere help to mitigate the damage. Large impacts can have catastrophic consequences for a planet's habitability. The energy released during an impact can vaporize oceans, blast away the atmosphere, and trigger global volcanic eruptions. While we don't have definitive evidence that such a catastrophic impact occurred on Mars, it remains a distinct possibility. Such an event could have dramatically altered the Martian environment, potentially wiping out any existing life and rendering the planet uninhabitable. Section 6. The Martian Water Crisis. Where did the oceans go? The evidence suggests that Mars was once a much wetter planet than it is today. Dried-up riverbeds, ancient lake basins, and minerals that form in the presence of water, all point to a time when liquid water flowed freely on the surface. The question of where all that water went is a key focus in our quest to understand the history of Mars. One possibility is that much of the Martian water is now locked beneath the surface as ice. We know that Mars has polar ice caps, but there might be vast reserves of ice hidden beneath the planet's crust. Another possibility is that the water escaped into space. As the Martian atmosphere thinned over time, the planet lost its ability to hold on to its water vapor. Ultraviolet radiation from the sun could have broken down water molecules in the upper atmosphere, allowing the hydrogen to escape into space, leaving behind a drier, less hospitable planet. Section 7. A toxic turn? Did poison end Martian life? Recent studies have suggested another intriguing possibility. The Martian surface might have become toxic, making it inhospitable to life. This theory revolves around perchlorates, a type of salt found in Martian soil. While perchlorates can be used as energy sources by some microbes, they are generally toxic to life as we know it. The high concentration of perchlorates in the Martian soil might be a relatively recent phenomenon. One theory suggests that these salts were once dissolved in Martian water. As the water evaporated or froze, the perchlorates became concentrated in the soil. Another theory proposes that perchlorates were deposited by volcanic activity. Regardless of their origin, the presence of perchlorates on Mars adds another layer of complexity to the question of Martian habitability. Despite the challenges, the possibility of life on Mars, even in the present day, remains an open question. While the surface seems too harsh for life as we know it, there might be more hospitable environments beneath the surface. Subsurface aquifers, shielded from the harsh radiation and extreme temperatures of the surface, could potentially harbor microbial life. Furthermore, certain types of extremophile organisms, found here on Earth in extremely challenging environments like deep-sea hydrothermal vents and acidic hot springs, demonstrate that life can thrive in conditions we once thought impossible. If extremophiles exist on Earth, it's conceivable that similar life forms could have evolved on Mars, finding ways to adapt to the planet's harsh conditions. The study of Mars holds valuable lessons for understanding our own planet's fate. While Earth and Mars evolved differently, they share a common origin and many similarities. By studying the factors that might have led to the loss of Mars's atmosphere and water, we gain insights into the delicate balance of processes that maintain Earth's habitability. For example, understanding how Mars lost its magnetic field, which is thought to have played a role in atmospheric stripping, can inform our understanding of Earth's magnetic field and how to protect it. The lessons learned from Mars can help us develop strategies to safeguard our own planet's environment and ensure its long-term habitability. The quest to unravel the mysteries of Mars continues. Future missions are planned to further explore the Martian surface and subsurface, searching for definitive signs of past or present life. These missions will deploy even more sophisticated rovers equipped with advanced instruments capable of analyzing Martian soil and rocks in greater detail. Perhaps the most ambitious goal is to return samples of Martian rock and soil to Earth for in-depth analysis. This would allow scientists to study Martian materials in laboratories with cutting-edge equipment, potentially revealing clues that robotic missions might miss. These future missions hold the promise of finally answering the question, did life ever exist on Mars, and if so, what happened to it? The exploration of Mars is more than just a scientific endeavor. It's a reflection of our innate curiosity and our desire to understand our place in the cosmos. The red planet serves as a reminder of the vastness of the universe and the possibility that we are not alone. Whether or not we find definitive proof of past or present life on Mars, the search itself is a testament to the power of human ingenuity and our enduring fascination with the unknown. The lessons we learn from exploring Mars will undoubtedly shape our understanding of the universe and our place within it. As we continue to reach for the stars, Mars will forever hold a special place in our collective imagination, a symbol of our quest to explore the cosmos and unravel the mysteries of the universe.